Okay, Physics 12, so this will be the video lesson that goes with the escape velocity, gravitational fields, potential energy lesson. Okay, so we'll just get into it. Okay, so as mentioned, this one's going to go over gravitational fields and escape velocity, and it kind of also talks about just gravitational potential energy in here as well. So we'll just kind of work through as much as we can and do the derivations and the examples together. Okay, so when we actually discuss a gravitational field, when we talk about fields, we are defining them as an area of influence. Okay, so there's lots of different types of fields, electric fields, and in this case we're talking about gravitational fields. Fields can have either two classifications. They can either be vector fields or scalar fields. And since gravitational fields are force fields, because there are forces being applied to them, they are considered vector fields. Okay, and that gravitational field that surrounds a mass and the vectors pull towards the center of the mass, right? Very similar to what we've seen already with centripetal force, right? Where objects are being pulled towards the center of that circular mass. The same kind of thing is true here now for gravitational, okay? So the idea of that common gravitational field strength, okay, we're most familiar with that in the terms of like lowercase g, right? So that idea of acceleration due to gravity on Earth, which we kind of know it as that constant of 9.81 newtons per kilogram or 9.81 meters per second squared, that constant of g, where the force of gravity, right, the gravitational field strength is the mass of the object on Earth multiplied by the gravitational field strength. Right, so force of gravity would be that mass of the object times the gravitational field strength, which we've always used as 9.81. Right, but we also know that g is not actually a constant for everything. Okay, so when we talk about that gravitational field strength of g, we have to remember that g, in fact, is only constant on a particular planet, right, or a particular surface. Okay, so since g is going to vary with the it's going to depend on the mass of the planet that you're on, and it depends on the distance between the objects, okay? We actually have to kind of look at a different value of g, right? We can't just automatically assume that it's always going to be that 9.81, okay? So if we kind of look at that first starting formula where we have that Fg is equal to mg, we'll do this one on the board. Okay, so that's kind of where we're starting at here, right? This is what we know. And if we're just trying to define that value of g, right, that gravitational energy, right, we're trying to figure out, well, what else can we get that as? If we're not going to use it as a constant, what can we use it as? So we just rearrange this formula here. We can divide both sides by m, and we get that g is equal to f of g divided by m. Okay. And in our work that we've been doing on universal gravitation, we have a different definition for f of g, right? We've seen as well now that f of g, right, that gravitational force can be defined as the force between two objects, where it's that universal force of gravitation multiplied by the two masses divided by the distance between them squared. Right, where m1 again is always that the larger mass that you're kind of orbiting around, and then m2 is the smaller mass, the object that's being orbited. So orbiting. So if we think about that, this is the object that's orbiting, or this is the object that's kind of on the planet of the smaller mass. That means if we're dealing with this formula here, this is going to end up being m2. Okay, this is depending on like the mass of the object. Right, on Earth, right, with the gravitational. So this is, again, like the mass of the smaller object, the object that's doing the orbiting per se. Okay, so if we kind of take this, right, and then substitute it in here, what we get is that gravitational force there is going to equal universal gravitation, m1, m2, over r squared, and then also over m squared, so that m2, and that goes there. And what you see there is that your m2s end up canceling, okay? So the mass of the actual object on the planet, or the object that's orbiting, is kind of irrelevant in this case. So g can just be termed as universal gravitational constant multiplied by the mass of the large object, right, the planet that we're on, or the thing that we're orbiting, right, divided by the distance between them squared. Okay, so that can be kind of our new definition for lowercase g that we can deal with. Okay. All right, so that is something that we'll definitely use. So let's use that now in another example. So if it's asking us what specifically is the gravitational field strength on the surface of the moon. Okay, so using that formula that we just came up with for little g, which is the gravitational field strength, okay, we can set that up in a similar way. Right, so we're trying to find that value. The formula we just derived was that gravitational field strength is universal gravitational constant multiplied by mass 1, or the mass of the object that we're dealing with. So in this case, it would be the moon divided by the radius, again, of that object squared. So we look at our fact sheets to get the values that we need here. So we've got our universal gravitational constant as our 6.67 times 10 to the minus 11. We can look up what is the mass of the moon. The mass of the moon ends up being 7.35 times 10 to the 22 kilograms. And we divide that by the radius of the moon, which again we can look up and have that as 1.74 times 10 to the 6. Right? And then that is squared. Right? You plug all that in, again, super carefully with your calculators, doing whatever process works for you, and you end up getting a value here of 1.62. And technically with the way the units would work here, the units here would be newtons per kilogram, right? Because this, right, that universal gravitational constant, that had units of Newton meters squared over kilograms squared, right? This is the mass in kilograms, so you'd be multiplying that by kilograms, right? And then you're dividing by a distance in meters squared, so you're dividing it by meters squared here. So if you take a look at what cancels in that sense, this kilogram cancels with this one, this m squared cancels with this m squared, and that gives you newtons per kilogram. But using your definition of a newton, which is a kilogram meter per second squared, right? That's the same as 1.62 times kilogram meter over second squared, and that's all over kilograms. And again, you notice the kilograms cancel, so that's where you get that same idea with the units of acceleration of 1.62 meters per second squared. Okay, so just kind of a quick review there with your unit analysis and making sure that you can get the correct values there. Okay, so there's your universal, your gravitational field strength of the moon, using that formula. Okay, so moving on, talking about gravitational potential energy, which will be very, very helpful when it comes to us to try and figure out what our escape velocity is for something. Okay, so we should already be somewhat familiar from Physics 11 or previous physics courses with the idea of gravitational potential energy, where the potential energy of a particular object is going to come from its mass multiplied by the gravitational field strength multiplied by the height. And again, previously in these other examples in our other learning, we would have used that g as acceleration due to gravity on Earth. But again, we know that that's not always the case because it's going to depend on the mass of the actual planet and the distance between the objects. Okay, so while this formula here is certainly useful, it's only useful where the distance between those kind of objects is, relatively small, like maybe a couple, kilometers at max. Okay, and then also the fact that we need to know this value, right? So this can be used fine when it's on Earth, but we would have to consider the planet. Okay, so when we're talking about more gravitational potential energy of things that are very, very far away, okay, we need to kind of think of this just a little bit more in depth. Okay, so in this case, we're going to derive again a new formula. So this is where we're starting with this gravitational potential energy. So I've used EP, other textbooks, and I think other notes might use EG, and I think even within the slide, I've switched to EG as well. They are kind of interchangeable, right? Like potential gravitational energy, so that's where the P is coming from, or just gravitational potential energy, that's where the G is coming from. So they kind of do interchange, just be kind of aware of that. Okay, so what we start with, switch to the whiteboard again to show you this derivation. Okay, so what we start with is this, okay, yeah, it's all good, this is our MGH, okay? And typically we would have just put in our 9.81 here, but we can't do that anymore, so we instead use that value of G that we've just defined, right, and derived, where that value, that gravitational force value, is the product of universal gravitational constant multiplied by the mass of that larger object or the planet divided by r squared, and then it's multiplying by the height here. But something to note is that when we talk about the radius here, we're talking about the distance between those two masses, right? So let's talk about, just a satellite that's in orbit, right? Where m1 would be the mass of the Earth, and the radius is going to be the distance, right, from that value, okay? And what's happening here is that the height of that object is essentially saying, well, what's the distance between the two objects, which is going to be the same, it's equivalent to our radius. So really, we can just substitute that value of h and actually call it a value of r, right? Because they're being defined as the same thing, right? That height is actually the height between the actual object and the center of the mass of the larger object, so let's say the Earth, okay? And then that's also how we've defined the radius in this case. So you can replace that h with actually an r, and then this cancels, right? And what you're left with instead is that gravitational potential energy here is just going to equal, and the other thing I meant to mention here is that this is actually technically m2, right? Because this would have been the mass of like the object, so like mass of the satellite. So what you end up getting here is this g, product of the masses, just divided by a single r. But what we actually note and how we actually write this is with a negative sign. And we'll explain that in the next slide. All right, we're essentially saying here that the gravitational potential energy is going to be negative in all situations, right? So we're going to define it as a gravitational potential energy. We're going to consider it as a negative value. And let's discuss why. And again, it's always going to be due to reference points, right? So much in physics is about, where are we referencing values? So when we discuss gravitational potential energy, obviously there has to be a reference point. And when talking about the potential energy on a mass provided by that gravitational force by a second mass, 0 is the reference point when the distance between the objects is infinite. Essentially saying that, well, there is no gravitational potential energy pull, right? There is no force connecting them potentially if the objects are infinitely far apart. Okay? You pull something so far away from the other object that its potential gravitational energy to pull that object closer to it is gone. All right? That's when it's 0. So when the objects are infinitely far apart, that's the 0 part. Right? Which means as that particular object might come closer and closer, the radius, the distance between them gets smaller and smaller. Compared to that infinite distance of the energy at 0, every other distance is going to cause a negative potential energy because it's being pulled back down towards that main object. Okay, so it's about that idea of reference point. And the reason it kind of does this is when you look at it mathematically, when these formulas are derived and they use calculus and they use area under the curve and they're looking at the actual curves, you get a little bit of a graph that looks like this that just kind of shows you that here, as your radius value increases and approaches infinite, you essentially get this asymptote where that potential energy, and again, you see that this one uses EG and not EP, they're interchangeable here, okay? This is approaching 0, right? But every other value of r, right, the distance between the objects, getting smaller and smaller and closer together, these values become more negative. Okay, so that's why we assign them the negative value. Okay, so let's then take that formula and apply it, right? So that means when we're trying to find that gravitational potential energy, right, or the gravitational potential energy, we should be getting negative answers. All right, so just kind of keep that in your head because it's being pulled down towards that object, right? So that's if you're trying to move something and its motion is going upwards, the gravitational potential energy is pulling it down, which is why it's going to have that negative value. All right, so let's look at this example. So what we've got is a 2,500 kilogram satellite that's in orbit, 3.60 times 10 to the 7 meters above the Earth's surface. It's asking what is the gravitational potential energy of the satellite due to the gravitational force of the Earth. Okay, so again, we have a formula now that we can use, so let's get to it. All right, so again, things that we've been given, right? The satellite would be our smaller mass, right, or our orbiting object. So that's going to be the M2 value at 2,500 kilograms. M1, we're orbiting around the Earth, so we would use the mass of the Earth constant of that 5.98 times 10 to the 24 kilograms. Okay, the radius that we need to use in this question is, again, the distance between the center of the larger object and the satellite itself. So our value for r that we're going to use is going to be the sum of the radius of the Earth plus the height of the satellite. Okay, so radius of the Earth, again, is the constant that's on our sheet, or we can just look it up if we need to, which is that value of 6.37 times 10 to the 6 meters, and we're given in the question that the height of the satellite, that's its height of its orbit, is that 3.60 times 10 to the 7 meters, which when you add those together, you get a value of 4.237 times 10 to the 7 meters. Okay, so we'll be using this for our M2, this for our M1, and this for our value of R. Okay, so that value of the gravitational potential energy, so EP or EG, that comes from that formula, negative G, product of the masses, divided by the radius. Okay, and then we just start plugging in values, right? So negative, put in your universal gravitational constant, put in your masses. I'm going to run out of space. Okay, 10 to the 24, all over that value of the radius, which we have there at the 4.237 times 10 to the 7. Okay, multiplying that all out, right? So that's the negative 6.67 times 10 to the negative 11 multiplied by 2,500 multiplied by 5.98 times 10 to the 24 divided by the 4.237 times 10 to the 7. Multiply it all out, do the divisions, and you should get a value there of negative 2.35 times 10 to the 10, and energy is in units of joules. Okay, so that's the potential gravitational energy of that satellite orbiting the Earth at that height with that mass. Okay, so that's, like I said, that's your gravitational potential energy of the satellite there. Okay, so that's that value again, negative, because it would have been pulled down toward the surface based on our reference point of 0 when they would be infinitely far away. Okay, so in a continuation of that same example, we can also ask, okay, well, what's the total energy of that satellite then? Okay, so just like we've seen before in other years where we're talking about like total force or net force, we need to talk about the total energy here of this satellite. And the satellite's energy, right, its total energy is a combination of its gravitational potential energy, and since it's a moving object, its kinetic energy. Right, so we have its gravitational potential energy, EP or EG, and then we have its kinetic energy to think about. Okay, so you might recall that EK, right, kinetic energy has that formula of 1/2 mv squared. And as we do that, we realize, oh shoot, we're going to need the velocity of the satellite, right? And we did that in the last lesson, where we know that the velocity of the satellite can be calculated, right, where v squared is equal to universal gravitational constant times m1, so the mass of the satellite in this case, mass of the Earth, sorry, m1 is always the mass of the thing you're orbiting around, divided by the radius, right? So we can use that. So let's go back to the board and get that done. Okay, so I've already kind of written out there, right, that our total energy is going to be the gravitational potential plus the kinetic energy. Okay, this value we just calculated in the last section, right? So we know that that has a value of the negative 2.35 times 10 to the 10 joules, and this is from the formula 1/2 mv squared. Okay, and we just concluded that, okay, well, to get the velocity, right, the velocity is going to come from, let's see if I can kind of fit it down here, right, using that formula we derived last time, where it's the square root of g times the mass divided by the radius, right? And then that can get substituted here, and actually if we're just trying to solve for v squared, we can then just get rid of that value there, okay? So what can then happen is we can solve for this, right, using our gravitational constant. That's 6.67 times 10 to the negative 11 multiplied by your mass of the Earth, which is going to be your 5.98 times 10 to the 24. Let's see if I can get this in a better spot, right? So I'll just maybe do a side note here, sorry. So your V is going to be your 6.67 times 10 to the negative 11, right? Gravitational constant multiplied by your mass of the Earth, 5.98 times 10 to the 24, okay? All divided by your radius, which is our 4.237 times 10 to the 7, right? And again, that wasn't radius of the Earth, but the height of the actual entire distance from the Earth all the way to the satellite, right? And then that would end up being square rooted. You do all that math, you get a velocity there of 3,068 meters per second. So that value can get substituted in here. Okay, sorry class. The remote should be up next to, like, in the little cubbies. Okay.
What cubby?
Like where we sometimes put the snacks. See if you can find it. Or on the top shelf. Check the top shelf. Okay, sorry about that. So anyway, that value of that 3,068 meters per second would go in there for velocity, right? So then, again, your mass of your satellite is going to be your 2,500. So again, your total energy is, there's our gravitational potential energy, and then this would be calculated as the 1/2 times the mass of the satellite at 2,500 multiplied by the velocity, which we calculated to be 3,068, and that value gets squared, okay? So that ends up giving us the following, right? So the kinetic energy of the satellite then ends up being this 1.176 times 10 to the 10 joules, and then you're just adding these two values together for a total energy of the satellite at negative 1.17 times 10 to the 10 joules in total. Okay, so a few formulas within formulas there. Okay, so again, we had to, in order to find the kinetic energy, we needed the mass of the satellite we were given, and we needed the velocity of the satellite. We could find the velocity of the satellite orbiting Earth because of this formula that we derived from our last lesson, right, where it was the square root of g times m1 divided by the radius, or the height between the two objects. Okay, so we can find it, sub it in, and then calculate away. All right, carrying on. All right, so that brings us directly into then escape velocity. Okay, so that idea of total energy, right, being a combination of your kinetic energy and the gravitational potential energy, is what's going to help us with our idea of, what's the escape velocity, right? So we have that general idea where, if you throw a rock up into the air, eventually it falls back down. You give it higher, you give it more velocity, right? You fire a bullet up into the air instead. Well, of course, it's going to go higher, it's going to take longer, but it eventually still comes back down. So it's that same idea when we talk about Newton's cannon, right? It's like, what would the velocity be of that cannon that you need in order to orbit? Well, let's take that one step further. What's the velocity required in order for it to escape the orbit of the Earth, right? So that it completely is gone and it's never going to come back down, meaning there is no gravitational potential energy acting on that particular object, okay? So again, as your object is leaving the surface of the planet, right, and exits the gravitational field, there's obviously a change in the gravitational potential energy and, of course, in its kinetic energy, right? So as we kind of just generally think about that, its gravitational potential energy is going to become more closer to zero, right? So it is, it's kind of increasing, but it's becoming just less negative, essentially, right, and closer to zero. And its kinetic energy would also be slowing down, so it would also be coming to zero as well. So if you think also about the context of the conservation of energy, what we've got is kinetic energy and the gravitational potential energy on the surface, and then somewhere out in space, right, or wherever it is, it's that second, or we can call it E prime, the kinetic energy, and then the gravitational potential energy here as well, right? These are the primes just being used as a separate point in time, right? Instead of using 1 and 2, we're just using just regular and then primes, okay? So if we're thinking about this idea of escape velocity, well, we don't want the object falling back to Earth, which means we don't want the Earth to have any sort of gravitational pull on the object that we've now sent out into space, which means we want this value to be nothing, right? We want this to have zero gravitational potential energy. And at the same time, if we've applied that minimum amount of energy to get it out there, right? If we're trying to say, well, what's the minimum velocity I need to get it to escape? Well, we're going to be sending it out, and its velocity from the beginning is going to decrease as it gets out there, and once it's there, that would also be zero as well. Okay, so using that, we get another wonderful little derivation, which looks like this. Okay, so again, what you've got is your EK plus your EP or EG equaling to your EK prime and your EP prime. Again, sometimes you'll see these interchanged with G's. They are the same thing. Okay, we just talked about how if we want escape velocity to work, then eventually the Earth will have no gravitational pull, so that will be reduced to zero, and it'll come to rest, meaning its kinetic energy will be reduced to zero, meaning that the original kinetic energy of whatever the object is that we're sending and its gravitational potential energy is just going to have to equal zero. So we have formulas for both of these. So our EK is our 1/2 mv squared, and again, this would be the mass of the object that we're sending, so that would be m2, plus our formula for EG, which is our negative gm1 m2 over r. Right, so the sum of those energies would need to equal zero. Obviously, then we can bring this over and it would become positive. All right, and then what we notice is that m2, so the mass of the actual object, is going to cancel. We're trying to find that escape velocity, so we can start by dividing both sides by 1/2, which is the same as multiplying by 2, so we get 2gm1 all over r, and then if we actually want the escape velocity, we just need to square root that. So our escape velocity is the square root of 2 times g times m1 over r. Okay. What I also want you to notice at this point as well is that your escape velocity does not contain m2 in the formula. So it doesn't matter what the mass is of the thing that we're trying to send into space, right, so that it can escape the Earth's orbit. That mass kind of is irrelevant. The velocity is dependent more on the surface that you're trying to escape from, the radius of the surface you're trying to escape from, right, and the universal gravitational constant. However, if you were being specifically asked about what's the kinetic energy of that object, that's where your m2 comes into play. Okay, so when determining that velocity, escape velocity, right, it doesn't matter, right? That mass of whatever it is that we're dealing with doesn't matter. However, it does matter for solving for kinetic energy, right? Solving for EK. All right, back to the slides. Okay, so there's that same derivation. Again, you'll notice this one uses EG. It was just already nice and typed up, and it saved me the time to just copy and paste it, right? And then their VE, right, is escape velocity, right, radius of the planet, right? That's what those things are. They're using a big M for the larger mass, little m for the smaller mass, right? So M, big M, kind of like for the big mass of the planet, and then little m for like the object that's on the planet. It's just slightly different notations, right? But the math all works out. Okay. So let's just kind of use that now to find the escape velocity, right? Let's see what that escape velocity from planet Earth is. We're talking about that, what's that movie, Escape from Planet Earth or something? Is that a thing? Feels like it might be a kid's movie. I've watched too many cartoons. Okay, so if we are going to look instead at finding the escape velocity of a rocket on planet Earth, again, we don't need to know the mass of the rocket because it's not in the escape velocity formula. So we use the formula that we just discussed, where escape velocity is equal to the square root of 2 times the universal gravitational constant multiplied by the mass of the Earth, right, or m1, divided by radius. And this just becomes a plug and chug, right? 2 times your 6.67 times 10 to the negative 11 multiplied by the mass of the Earth, which is again on our sheets of 5.98 times 10 to the 24. All divided by the radius of the Earth, which is that 6.37 times 10 to the 6. Right, we don't need to add any other sort of heights because we're talking about escaping from Earth, so we're starting on planet Earth. We don't know what height this is going to get to at this point. And we plug all these numbers into a nice calculator, doing so as carefully as possible to make sure we don't have any mistakes. And we get a escape velocity of 1.11 times 10 to the 4 meters per second. All right, do with that what you will, and turning it into kilometers per hour, etc., but there you go. Okay? So the only other thing to kind of finish off here is a connection between what we've already been talking about as the gravitational potential energy as well as something called binding energy. Because you'll notice that the binding energy formula here is the exact same as that gravitational potential energy, but it is actually considered positive, right? Because when we talk about the gravitational potential energy, right, we're talking about it as being pulled down to the Earth, right? So that's acting as a negative value. But if we just talk about it as the binding energy, right, what's the energy that's keeping something on Earth, then we can kind of think of it as the positive value, right? So again, if we think of the total energy of an object as negative, right, it's obviously going to be bound to the Earth, okay? And therefore the binding energy of any mass is the amount of additional kinetic energy it needs to escape, okay? So if we're trying to escape, right, so if we're not moving and we're just being bound, that's our value there. And then to escape Earth's gravity, the total energy, yes, you can have the Smarties, sorry again. So to escape Earth's gravity, the total energy must be reduced to 0, right? So if we want this value here to be 0, then what we would need to do is add this back in. Okay, so that's the binding energy. So just kind of like a nice little connection there. And same kind of thing in terms of like binding energy in orbit. So something in orbit and it's not completely, gone, then there is still some of that gravitational potential energy, and there's kinetic energy as well because it is moving, right? It's not stationary on Earth, it's rotating in orbit there. Then your total energy, again, is a combination of its kinetic energy and its gravitational potential energy. So again, if we want the binding energy, right, so we want it reducing the total energy to 0, right, what energy is required to get it to be bound completely, right, what you'd end up having to do is add the opposites there, right? So then this term would be negative and this term would be positive. So that would be the binding energy there. Okay, so just kind of a neat little extension connection there in terms of binding energy. Okay, that's it. What you've got in terms of practice problems here is an escape velocity worksheet that's been posted with solutions posted as well. You do get practicing calculating escape velocities on different planets, etc. Solutions have been posted there, and then once you're done that, you're able to start working on your actual assignment for hand-in, right? And that's being handed in on Wednesday, okay? And any time on Wednesday is fine, right? So like essentially what you've got now is, if this is being posted by this afternoon, you've kind of got Monday night to chip away at the assignment or worksheet, then you've got Tuesday and Wednesday to kind of work on that. So hopefully that's fine. If it's not, please reach out, let me know where the issues are, and we can discuss a suitable thing, right? But on Thursday, I'll have another video posted so that you can get started on our next unit, right? Because this is actually the end of our universal gravitational kind of energy section. Okay, so apologies for the interrupting child. Do what I can, but 'tis not easy. Yeah, there we go. Okay.